So without further ado, Michiel, the floor is yours.
Yeah, high expectations. When is the third movie ever the best movie of a trilogy, right? Um, okay, so like David said, the third session in our series of color cafes. I'll do a quick recap in the next few slides. Today's series is about using all the information we learned about in the previous two sessions. So if you were there, congratulations and thank you. They are available on YouTube. I see we have gotten some views already. We even have some people leaving comments. I really appreciate that. So if you have something to say, something to add, feel free to add something to those videos. And if you haven't seen them, or if you weren't present at the cafes, please go and watch those two as well. This one will be available if you want to rewatch it later. So, color and hue. The last time we're going to see this wonderful intro slide. And this is what we have seen so far. So we started this series off with deciding, well, looking at what is color really. Then we talked about communication about color. And now we're going to use the information we learned to make it into color management. Quick recap, we started off by having the spectral power distribution graph for light sources. So basically the light that is coming in that has certain amounts of each wavelength in it. These wavelengths correspond to spectral colors. Then we have our object, which has a certain reflectance graph. So the color that object is reflecting, so the color we see the object as, like our red apple. And then we have the human observer who has the color matching functions that were created to help us quantify the human vision of color. All of these together give us mathematical information, numeric information on what a color really is for each object. Then we have our naming systems where we decide how to talk about colors. We had to give a color a name, or even better, we can give these colors coordinates on a color system. So we have our naming systems like anything that has a specific color name, or for example, the Pantone colors. And we have our color systems like XYZ and LAB that help us define colors using coordinates on a system. And that gave us a way to talk about color with a certain accuracy. But now that is when we talk about color between people. In reality, when we're talking about our industry, usually what happens is it's machines that talk about color. It's how to communicate color between a camera or a designer who is creating something and a printer who is reproducing it in a certain way. And we're going to talk about that today. I have a slide here that I also used in the previous presentation, where we have our device-dependent color spaces on the left, like screens, cameras, the internet, or printers, and we have our device-independent color space on the right. Last time we focused a lot on the device-independent color spaces like XYZ and LAB, which can be used to define a color unequivocally, which means that everyone who has that information can interpret that color in the same way. Today, we're going to focus on the device-dependent color spaces. I have another quick slide going over the device-independent color space. This is based on spectral measurements. This is theoretical, and you can define any color in that color space, which makes it good to use. Device-dependent color spaces, again, are, for example, your camera, your screen, and your printer. Why are these device-dependent? Because every device will use color in its unique way. The colors registered by your camera, the colors printed by your printer are unique for that device. These are based on RGB or CMYK. Now, while RGB and CMYK have those primaries and you can define a color by those primaries, actually what's happening is if you enter those primaries in a device, it will reproduce it using those quantities of primaries. But you don't know what the maximum color of those primaries actually results in from that device. When you look at RGB, we have an additive color space. We already discussed this in a previous session as well. We have our three primaries, our red, our green, and our blue light. And when we add those together, we're adding light, so we get a brighter color, eventually resulting in white. Usually we note RGB colors using an 8-bit information, so values between 0 and 255. And then we have, this is used for cameras who are recording light information using a sensor that has filters for RGB. So all the light falls on the sensor. There are filters on each pixel of the sensor that is filtering out either the red, green, or blue light, and that gives us that information in that sensor that is able to interpret that as colored pixels on your image. And the screen is doing the same thing in reverse. So you have red, green, and blue light sources in your screen in each pixel. And the amount of light that is executed from each of those pixels gives you a resulting color on your screen. Then we have our CMYK color space, which is a subtractive color space. So while in an additive color space, when you add more primaries, the color gets brighter because you're adding light. In a subtractive color space, when you add extra filters, because the ink is acting as a filter, you're blocking more light, which means that the resulting color is darker. So our primaries are quite bright, and as we add primaries, we get a darker color, eventually resulting in black. Now, in a theoretical perfect world, cyan, magenta, and yellow primaries result in a perfect black. But in practice, that's not true. We get a dark gray brownish color when we add our three primaries. So we have our key color, our black, that we add to the mix to fill up that gap and to help us reach nice dark blacks. CMYK is usually presented with a 0 to 100% value, 100% being the max amount of ink you can put on your plate. Of course, we have linearization happening and stuff like that to see which amount of ink results in the darkest color, but we'll get to that in a few slides. And then we're talking about the profiling. So after there we go. So that's for printers. And CMYK, it's just like with RGB. I only have one printer icon there, but each printer will have different results using the same CMYK values, because 100 cyan and 50 magenta on one printer will not give the same LAB results as it does on another printer, which is using different inks, for example. So we have to do what we call profiling. Now, profiling for RGB and CMYK is essentially the exact same process. What's happening is the exact same thing. We have to start by creating a chart that contains patches of colors defined in that system's primaries. So each of the patches on the screen are defined by a certain combination of RGB. Of course, we need to have the primaries themselves. So we need to know what is the maximum amount of red, green, and blue we can generate using that machine. So we have a patch for full red, full green, full blue, and nothing else. We also need to know our white and our black points. So we have those as well. And then we have patches for a lot of colors in between. Depending on how many patches you make, you'll have more information that you can use. Now, all of these patches, if we spread them out into a theoretical color cube, you see they're pretty much evenly spaced throughout the color space. So the difference between each of these patches is pretty much the same. Now that we have all those colors defined by RGB, that still doesn't mean they have value. That just means that we can produce those colors with those color values. It doesn't mean that have any weight behind it. We have to measure them first. So when I use my spectrophotometer and I measure the spectral reflectance or the color emitted by my screen for each of those patches, I can match up the RGB primaries with LAB results. And if I go back and forth between these slides, you might see that the color patches have a slight difference in their actual colors as well. And we see that the red color, for example, is a certain L, a certain A, a certain P value. And we have to do that for all of those patches. At the end, that gives us a table that matches up certain RGB primaries with certain LAB results. Of course, we can't measure every color. We can't measure every single RGB combination. So what we do is we measure a set of them, and then we extrapolate and interpolate the rest of the values. We do some assumptions, and we can create a table that is able to convert basically any primary to LAB. And then if we take that same cube we had before after measurement, you see the points are put where they actually are in an LAB color space, and they give us the more typical 3D view that we would have for such a color space. Now, I told you it's the same process for CMYK. So you see here we have a chart set for CMYK. Again, we need to define our primaries. So we have a full primary patch for CMYK, and you can see the values for them. Obviously, it's just 100 for the color that they're supposed to be. And then we have our 0 and our 100 patch, so our completely white and our as black as possible patch. Now, normally you probably won't print in CMYK 400 total ink coverage, but we can still measure all these colors and see what kind of results we get. Again, we can put them in a theoretical cube, so you see where the patches all end up, and then we can measure all these values after print. So I think Zoom got active again. There we go. We can measure those colors into a result. And you see here, it's very obvious how different the color becomes between my two slides. The primaries here are a lot darker. That's because the measurement values I used are from a digital printer. And digital printers oftentimes have very, very strong color. So the colors here become quite dark. You also see that white and black have certain values. So if you theoretically would say white is white, you would have 100L and then 0A, 0B. That would be a very neutral, strongest possible white. But in these measurements, my 0000 patch isn't actually white. It is the paper color. So you have to take into account that that paper color also has an effect on everything you print on top of it. And that's why the L patch here, apparently this is slightly bluish paper because it has a slightly negative B value. Bluish paper is of course quite typical in the printing industry. Now we can make that table and we can connect our CMYK primaries with our LAB results. Then, of course, there's variables. Now we have our tables. We did our profiling. We measured our patches either from our screen or from our print, and we put them together with our LAB value. So we have our conversion table. We have a profile for our printer or for our camera or our screen. That isn't necessarily true in every way. There are variables involved. Our profile is only valid for that single device in its current conditions. For a printer, those conditions would obviously be ink and paper, right? When you have different inks, those inks have different colors, different pigments, that has a different result. So you have to consistently use the same ink or toner. With offset, you have a few choices between ink manufacturers. With digital printing, you're probably stuck with the ink you get from the manufacturer of your printing device, although there's usually a third-party cheaper option you can pick as well. You have to make sure that you use the same variables when you're using the same profile. Other variables people don't really think of are the humidity in the room and the temperature in the room. A higher humidity will have an effect on your paper. A higher temperature will make your ink less viscous. So that will also have an effect on the resulting print. So those are also variables you have to take into account. Another variable would be the amount of coffee the printer had that morning. But of course, you can't really standardize that too much. Now, all of these variables, if we want to keep them consistent, that results logically in calibration. So what is calibration? It is where you would standardize those variables to a certain set, so you don't have to keep making new profiles every day, right? So we would take our ink, we would take our paper, we would take our humidity, our temperature, and we would say, this is now a calibrated device, because every single time we print with this device, we are using these variables. And that way you have a printing profile that stays valid as long as you keep to those variables. And those variables, of course, bring us to standardized profiles. In RGB, you would have sRGB, Adobe RGB, ProPhoto RGB as examples. Of course, you won't have a lot of impact on that. Those are typically the RGB color spaces that are used by your camera. If you make pictures with a camera, the most default RGB color space would be sRGB. That is also generically the basic RGB profile used on the internet. So sRGB is likely what you're going to get when you have RGB files incoming. Adobe RGB is used often by photographers, and the same is true for ProPhoto RGB. But it's not because a photographer uses ProPhoto RGB that that's the best color space for them to use when communicating with customers. Because if they make their profiles perfectly in ProPhoto RGB and then they send it with those values without an embedded profile to a customer who will view it in sRGB, their colors will look quite washed out, because the primaries in ProPhoto are stronger. So when you say 100 from a certain color, that will be worth less in sRGB than it is in ProPhoto RGB. And then in CMYK color spaces, everybody is aware of FOGRA 39, which is ISO-coded V2, FOGRA 51, which is the new PSO-coded V3 in the UK and in Europe. In the US, typically they use Crackle or Swap, which are the general requirements for applications in commercial offset lithography. I practiced that. And the specifications for web offset publications. So basically sheet offset and web offset. And that's it's the same in the European standards. You have profiles for either of those. You also have standard profiles for newspaper prints, for example. So these profiles are created based on standards, based on a typical set of variables for these devices. So if you want to print according to FOGRA 39, then you have to make sure that you're using the right inks, that you're printing them in the right density, that your machine has the right specifications, and that you're using the right paper. All of that stuff is defined in the ISO standards, the 12647-2, to make sure that people are able to use these standard profiles. If you're not printing according to those standard variables, then that profile isn't really worth anything to you. Then you have to create your own profile. And even if you are printing, these profiles are basically an average. They're an average set for all the printers that are using those conditions. So it might still not be a perfect match for your machine. You might still want to create your own profile, but at least they give you a common way of communicating with profiles between different people, between different producers. So we've talked about how to create a profile, how to create our translation table. Now we have to put all of that in practice. We have to put it together. So if my slides catch up again. Okay, there we go. We have to put it together. So let's start a little metaphor. Let's say we have a person who only speaks Dutch, and we have another person who only speaks French, and they want to talk to each other. Well, they're going to run into a bit of trouble. But the Dutch person has a dictionary that translates Dutch to English, and the French person happens to have a dictionary that translates French to English. Now they're getting somewhere. They can use English as a common language, and they can translate their words and make sure they understand each other by using the English language. And that's what we do when we create a profile. We take our, let me just end the metaphor there and put this aside. We take our incoming color space, which is our camera using RGB. We have our outgoing color space, which is our printers using CMYK. But both of these profiles we created have LAB as a common language. So we can communicate these colors through LAB. And that's what profiling is. So in practice, what we will do is we will have our color profile for sRGB, and we will have our color profile for ISO-coded V2, for example, and we will be able to convert our colors from our incoming point to our outgoing point. That all sounds really easy. Well, this is it, right? We're done. We can do color management. We just have to have those profiles and we're done. But it's still not that simple. It goes a little bit further because we've already talked about color spaces, right? And if I take my color space and I take my RGB color space, there we go. That's a pretty big color space. Now, if I turn that off again and I open up my ISO-coated color space, that's a bit smaller. So if I overlay these color spaces, we can see that there's a whole bunch of colors that we can reach in RGB. I think I'm having a slight bit of lag. That there's a whole bunch of colors we can reach in RGB that we can't reach in CMYK. So what if those colors are present in our table? What happens when we're trying to create colors in CMYK that just aren't part of our conversion table? Well, we have to translate them somehow. We have to make sure that we are able to do something with them. And that's where rendering intents come in. So if I go to the next slide, if it lets me, there we go. We have rendering intents. So again, let's take a color space. We have a really big, nice RGB color space. Let's take a second color space, which is not the same size. This is our CMYK color space. Of course, in practice, the color spaces aren't always perfectly enclosed. There are usually some dark blue colors, for example, that you can print in CMYK that you can't actually display in RGB. That all depends. So it's not always as perfect as the little diagram I'm going to show you now. But let's say we have 4 colors. I'll put my color spaces together to help with the visualization, and I put some colors on there. Now, as long as, let's do another metaphor. If you're talking about languages, there is this old urban legend, there's these stories that Inuits have 50 to 100 different words for snow, right? They have a word for wet snow, dry snow, powder snow, snow that is really good to ride on with a sleigh. They have all these words. But in English, what we would do is we would add adjectives. We would say, oh, that's wet snow. But we're using snow still as the word, and we add wet to it. As long as you have, as long as you're communicating and you're using words that exist in the exact same way, that can be literally translated between 2 languages, you don't have any trouble. So in this case, if I'm using these colors and I'm converting from RGB to CMYK, I can just convert it. It's done, it's fine. But what happens if I take colors that are partially outside of my spectrum? I'm using these colors in RGB that I can't reproduce in CMYK. I have to handle these in a certain way. Now, in practice, there's 4 rendering intents. There's relative colorimetric, absolute colorimetric, perceptual, and saturation. Now, you can forget about saturation because that one isn't important and it's not used in practice. The other 3 are. I'm going to combine colorimetric render intents together, and I'm going to show you the difference between colorimetric and perceptual. So if I want to transform these colors using a colorimetric rendering intent, what would happen is this. I can take these colors out so we can see the difference, and I can do my conversion. The 2 colors that were outside of my shape are put right on the edge. Now, of course, this is kind of an ideal situation where my 4 colors are in a perfect line away from the center, but this is how it would happen in a 3D space as well. The colors would be put on essentially the closest edge of my 3D shape. Now, in this case, that means that my 2 colors that were here on the outside are now the same color. Didn't mean to do that. They're now the same color in the result. So you will see some clipping, which means we will lose any differences in these bright saturated colors. But all the colors inside my little green circle here will remain accurate. They will remain exactly the same as they were before. So this is a valid way to convert colors in many cases. It depends on what you want for your result. If you want to have an as accurate as possible conversion, then you're likely to go for a colorimetric rendering intent because it changes the least amount of colors. But you might have some clipping in those really saturated colors. And then we have the perceptual rendering intent. So if I take the same 4 colors and I convert using a perceptual rendering intent, what will happen is the following. All the colors are scaled until the brightest color ends up on the edge. So in this case, we're transforming essentially every color, but we can still see differences between all the colors that were present in the file. So these last 2 colors aren't the same. They are still different, and they are relatively the same difference as they were before. And this is typically used in photography workflows, where the shadows and the slight differences in those saturated colors are a big part of it, and the accuracy of the conversion doesn't matter that much, or not in that much detail. We're not talking about huge differences here, but there will be slight differences between what the colors originally were. And that's what happened in rendering intents. So now, sure, David?
That means that, so if I unmute myself, you already stopped. That is very impressive. That means if I take an example, if you would make a pie chart with those 4 colors, and you use perceptual rendering, a perceptual rendering intent, you would still see a difference between the colors afterwards.
Yep.
But all 4 of them will be different than the original.
Yeah.
Yeah. While if you use the other rendering intents, you might not actually see any difference anymore between different parts of the pie, because they have been mapped to the same color, correct?
Yeah. But just like your example, my scheme on the slide is in a stupidly ideal world where I have 4 colors that are perfectly in line from the center of my color space to the edge and beyond the edge, so that they are converted in that direction. So that is something that in practice probably won't happen. But you might have colors that are very close together in a saturated range, and that just happen to end up very close together on the edge of a color space where you lose the visible difference between them.
You can also say that you, in perceptual, you keep the tonal range in a way.
Yeah.
Yeah.
So you get the soft transition from the over those colors.
Yeah.
Yeah.
So with the other one, you clip everything.
Yeah.
I should have added like a gradient on the slide. Like if you have a gradient with perceptual, you would still keep a complete gradient, and with colorimetric, you would basically clip the end of it, and you would have your gradient up to 80% and have 50% the same at the end.
Yeah.
That's kind of a good illustration, and I might add that to the slide later. So that now we're able to solve that problem. We're able to have our conversion table, and we're able to handle colors that aren't perfectly ideal in the conversion we're trying to do. So now we can do color management, right? And that's correct. Now we can actually convert colors between color spaces. Now we just have to look at different situations. And the typical situation that we're thinking of when talking about color management, someone just entered the recording again, so my slides are buggy again. Okay, so the typical situation we think of is when we have our camera, we have our printer, and we have our 2 conversions from RGB to a CMYK color space. Now, of course, when you use a tool to do something like this, you would just say, oh, I want to convert my objects to CMYK, and the tool will handle the rest of it. Now, where do the profiles come from? Well, on incoming files from a camera or from the internet, typically an embedded profile is present. So you have your sRGB profile attached to the image, and that way your system knows what they're supposed to be looking at. And if it's not embedded, then it's referenced. And if it's a typical standard color space, then you have enough information by knowing it's sRGB because you have it on your computer. So you don't have to worry about that too much. If you're talking about something like PDFs, you have an output intent which tells you which color is supposed to be in the file. And you also have the embedded color spaces for all the objects in the file. So you have all that information. So you can do that transformation, and your tool can handle everything just fine. Now, if we take that a bit further, let's say we have our one camera, we have our one printer, and we want to do that conversion. So no problem, we just take our LAB color space and we convert from our RGB to LAB and from LAB to CMYK. Okay, now if I have more than one input device, let's say I have maybe different cameras, or I'm using the internet, or I also want to use stuff that has a different RGB color space, no problem. As long as I have a profile for those color spaces, I can convert them to LAB, and I can use my same printer color profile to convert them to my printer. That works fine. The same if I have more printers. I can just convert from LAB using those printers' profiles to convert them to that printer output. No problem. So in this scenario, I only need one profile for each of my devices. I need one profile for each incoming and outgoing color space. That makes it kind of clean. But you're always doing two conversions. You're converting to LAB, and then you're converting to your output space. This gives you a very slight rounding error in some cases, and this also means that some colors might be converted in a way you don't always want them to be. For example, if you look at my CMYK primaries of my digital printer that we saw earlier, a color that is 100 cyan from that color space converted to a FOGRA 39 CMYK color space would not result necessarily in 100 cyan. It might be 100 cyan plus 20 magenta, because it's a pretty dark color. Now, you might want to prevent that. And to prevent that from happening, we can use a different way of converting color. And we have what is called device links. There we go. So we have our one input color space, we have our one output color space, and we create a translation table that goes directly from one to the other. Of course, when creating this, you will be using the LAB references for those colors. So you start from two color profiles. You have your one color profile, which is your RGB to LAB. You have your second color profile, which is your CMYK to LAB. And you use a tool to combine those and to add rules to the conversion. And you create a new conversion table that is translating RGB to CMYK directly, skipping the step for the LAB. So if I have multiple printers, that means I have to create a translation profile directly from my camera to each of those printers. And if I have multiple input devices, I also have to create profiles from each of those to each of the outputs. So you see that becomes a huge mess. There's a lot of lines on the screen. I have to manage a lot of profiles. And if I buy one more printer, I have to create 3 more profiles because I have 3 input devices. So that becomes a little bit hard to manage. Now, there are still advantages to be had from DeviceLink. You're doing that one less conversion. You're doing the exceptions I just mentioned. So primary colors, for example, remain primary colors. That means the conversion might not be accurate because you're not translating through LAB, but it will probably be visually better than having that 5% magenta in your cyan that is causing the peppering effect and doesn't make it nice. So it's a decision you have to make for yourself. Of course, DeviceLink profiles are only valid between 2 conditions, between 2 devices. So typically they're used to convert between standards. That means that you can have a DeviceLink profile that converts, for example, ISO-coded V2 to PSO-coded V3, FOGRA 39 to FOGRA 51, which is interesting because typically as a print shop, you will get files coming in that are FOGRA 39. But you might be printing according to FOGRA 51, so you might have to do that conversion. And if you have a nice DeviceLink profile, again, you can keep your primaries pure. You can make sure that that conversion happens well. So DeviceLinks have their advantage. It just depends on your workflow, where you want to use them and how. Then I have one more example for a typical color conversion flow, and that's proofing. Now, proofing, of course, when you have your incoming and your production and you create your conversion, your customer typically wants to see the result because, as we know, we're shrinking the color space. So our output color is not necessarily identical to our input color. So we need to confirm with the customer that the result is okay for them. So we want to create proofs, but we can't just print a color proof on a CMYK offset press, because you have to start up your press, you have to make your plates, you have to print 200 sheets before you reach full color. So that would waste a lot of time. So we're going to try to simulate that offset presses color production on a digital printer that we can easily just say print. Now that means we're doing something like this. We're converting our color from our incoming space, whichever it is, to our production press. And then we're doing a second conversion, converting to our proofer. And here we have our two colorimetric rendering intents. So the difference between them is whether or not they take into account the white point. With relative colorimetric, you will convert the white point to the white point of your outgoing device. So white in my RGB is going to be white on my production printer. White on my production printer means paper white. So you will be printing on whatever the paper white of your production flow is. But if I'm printing for a newspaper and I have to print a proof for an ad that a company wants to place in a newspaper, I can't print that on my amazingly white/blue proofer paper, because that is not what it's going to look like when you print it on yellow newspaper. So I'm going to use an absolute colorimetric rendering intent to convert to my proofer. Absolute colorimetric will also simulate the white points of the previous color space. So it will simulate whatever the color white would be for my paper on my production and try to create that color on my proofer, which means that it's going to add some yellow to my print when there is no ink normally there, so you have the simulated paper color. That's a typical workflow that we would see. Now, of course, there's other workflows in typical scenarios, and you will have different tools that you can use for color reproduction. Now, you're probably doing color management. If I had added a poll here and I asked you who is doing color management, some of you might say, oh no, I'm not doing color management. But you probably are, because some of this is happening in the background, right? Like I said, your files likely already have color profiles embedded in them when you get them from wherever you're getting them from. And your output device, like your printer, also knows what color space generically it's supposed to be using. And something is telling your printer what to print in CMYK, even though you're pushing an RGB color space, probably the built-in RIP. So that RIP is already doing a conversion for you, and you are printing in CMYK what you had in RGB. Is that completely default color conversion that you're doing the best? Probably not, but it is happening and it is helping you behind your back. Now, there are other ways to handle it. You could do a color-savvy design workflow. So you could design your files in function of your output. If you're designing digital stuff and you're designing for print, you could already design your files in CMYK. And that is going to help you for print, because you're not going to use those colors that you can't print. Of course, that would mean you have to have a color calibrated screen if you want to be completely accurate, but that's just part of it. Then you can do PDF pre-flighting. You can check whether the file you're sending to print has the correct color in it. And if it doesn't, you can do a color conversion. Our Colors PDF Toolbox, for example, has a color engine inside of it that can do good color conversions to another color space. And then another option is having a color server. And a color server is essentially also a tool that looks at your incoming files, looks at what color they're using, and converts it to whatever color you want on the other side. It's just an automated version that does color conversions. Does everybody need a color server? Probably not. Not everybody has the need of that. Not everybody even needs to do that PDF pre-flighting. If you have a good color profile that you created for your RIP, and your RIP is able to handle color conversions properly, then that is probably already giving you a decent result. But now you at least know what's happening, and you can look into the next steps if you are trying to create, if you're trying to make changes to your color management workflow. I know I only went the tip of the iceberg on all of these webinars. So this is essentially the end of this one. I only went very basic, very high level on all of it, but that's kind of the point of these webinars. I can't go into detail for every possible workflow. But this will have given you a basic understanding of what people are talking about when they're talking about color management, about color profiles, about rendering intents, and what's actually going on in the background. So I hope that that all 3 of these sessions were interesting for you. If you have questions about specific scenarios, about specific workflows, do send us an email. Four Pees does do services also related to workflows and color management. So do send us an email and we will see if we can help and how. It's not a problem. If there are any questions right now, feel free to ask them as well. You can unmute yourself or put something in chat.
So I will start.
Yay.
Yes. Just to make it clear for myself and maybe also for other people, if you could go back to the slide where you had the proofing scenario.
I will try.
Yes, I know. Yes. So if we take an example of, let's take a picture that has, so photograph that has white color in it. Yes. What you're saying, if we're going to print that on a newspaper machine, we're probably going to print it on yellowish paper.
Yeah.
If I do this relative colorimetric conversion, I would end up with yellow instead of white for those areas.
Yeah, that white would be whatever paper whatever color your paper is.
Yeah. And what you're saying with the absolute colorimetric transformation is then that instead of converting it back to the white that your proofer can probably do, you're purposefully keeping it to the yellow, so it represents the same as what would happen on the production device.
Yeah, and you have to think of it in how the printer works, right? If you have white in CMYK, it means you're putting 0% ink for cyan, magenta, yellow, and black on the page. So you're putting 0 ink on the page, so you end up with whatever color the paper is. And if you do the same thing on your proofer, you end up with whatever color your proofer paper is. And typically your proofer paper is very white, almost blue. So you would end up with a different result. And you simulate the paper white by essentially printing a layer of yellow or printing a layer of a newspaper color on your entire sheet where you're printing, and then you're adding the other inks on top of that. So that's a different way of doing the color conversion.
You also have to think about that the reason for doing that is that the colors of the objects for the flowers or grass or cars or whatever are affected by the paper color. So the yellowish paper color on newspaper makes everything look yellowish. But your eyes are fooling you there because they think they're seeing it as white as well. But I mean all the colors in the objects on the page are affected by the paper color.
Yeah.
So that's why we simulated.
You're doing some chromatic adaptation in your head that is fooling you into thinking the neutral color is white, while actually it's yellow through the whole page.
Until you take a really white sheet and hold it next to it,
yeah,
and you see that it's not white at all.
But if you want to reproduce white on that newspaper, you could also do that absolute conversion first, right? And convert your white point from your start area to whatever you want to have as pure white on your newspaper. Now, are you going to print pure white? No, you're going to convert whatever the yellow is by adding blue to make it neutral. So you're going to get a neutral gray on your newspaper, which is going to be neutral, but everything will be slightly darker than it was because you're adding ink to it.
You can't print real white because you always have the paper underneath, unless you're using a spot color ink, which is
unless you're printing white. Yeah. I didn't do a lot about spot color conversion in this session because we did spot color conversion in the previous one pretty much. Spot colors are defined by a certain LAB value that they're supposed to represent. So, or even by a CMYK or RGB value, it depends what the alternate color space of a spot color is. So they have a connection to whatever you want to print, and you can just use that connection and convert it that way.
Yeah, and then there was, so thanks. And then there was one other thing I wanted to comment on, even though I know the answer, but you didn't mention it, and I think it's something that happens quite often. When you talked about DeviceLink conversions, you have some examples for on how and where to use them, and the typical case is, of course, converting from one standard to the other. I think it's worthwhile mentioning that a DeviceLink profile doesn't have to be between two different color spaces, but it can actually be between one and the same color space while doing some correction on the way.
Yep, absolutely, yeah. So typically what David is talking about would be for tack reduction, where you can reduce the amount of ink. And it's something you probably see a lot when you're talking about iso-coated and iso-coated 300%, for example, or you can go lower than that. You would recalculate your colors while taking into account an output space that was created with a maximum amount of ink that has a certain limit. So that's where you're doing a good conversion between the exact same color space, but you're using less ink at the end. The colors will be slightly different because you will no longer be able to print 330% of ink, but because you're doing an as accurate as possible conversion with that limit through DeviceLink, it's probably not going to be very visible.
There's another way also.
Mention two, I'm sorry, Jan. Maybe worthwhile mentioning two terms that come back in that area as well, and that we get quite a few questions about, and that is tack reduction and ink saving, where tack reduction has it's technically very similar, but tack reduction has is typically used to make sure that you can technically print a certain percentage of ink. So you're reducing the amount of ink because you don't want the ink to start dripping from the paper when you print with it, or the paper to fall apart. And ink save is more from it goes further. It's the same kind of technology, but it typically goes further, and it tries to print with the minimum amount of ink. So even if your device can print 300%, if you can reproduce the colors with only 150, then you will go down, or you could go down to 150. And the reasons there are economical on the one hand, of course, you're going to save money, but it could also be about ease of printing and print speed, because the less the paper has to dry, and so on and so on.
Yep.
Another way with the device links and profiles in general is that another factor is the black generation you have in the profile, the black point generation. So for really advanced image handling, you can have different black points and black generations for different type of images. Like skin colors, you would like to have less black into them, but other images could have a lot of black, and for that reason you can have different ICC profiles with different black generation, but all of them are for FOGRA 51, but they have different black generation, black curve. And that can make it really difficult when you come to a print job later on, because then you have maybe one document can have 4 different CMYK profiles, all for FOGRA 51. But you want to keep those images as they are. You don't want to translate them to the common standard one, because then you ruin all that job you have done on your images.
Yeah.
And in that case, you can use, if the printer knows about it, and they can create device links from each of those of your special profiles to the standard profile to get the images still looking good. But that's really advanced stuff, and you have to talk to your printer about.
Yep.
So they keep it like that, like you have done.
So you can see here on this slide that's 100K results in a lightness of 17, while 400% ink results in a lightness of 13. Well, I'm pretty sure that 300% ink will also result in a lightness of like 14. So those extra 100% ink that you're putting on top of that isn't really making a huge difference. And when you create your black point, you're typically looking for a bit of a sweet spot between handleable and the darkest color you want to get, as well as color impression if you're going into how much of each color is underneath it.
But hence why people want to print rich black as well, right? And not just use the black color, but add other colors in order to make it more black.
But you also have the black start in the profile, so the first 30% could be without black.
Yep.
And that's really important for a special type of images.
One more important thing that I haven't really mentioned is about the primaries, right? So I've talked about RGB and CMYK primaries. Now, of course, you can essentially do this with any primaries you want, right? You're not bound to RGB or CMYK. You have a lot of printers are using orange, green, or violet as extra primaries, or you could even create a profile that is using 4 completely different inks. As long as you can mix them together, as long as they're transparent, you can mix them together in a good way, then you can make your chart using percentages of those primaries, measure them in, make a link between what those primaries reproduce in LAB, and have a profile that tries to generate color in those primaries. We had cases at 4 Pees in support, people creating profiles for terracotta printing, where they had 4 primaries and 3 of them were essentially brown. But it was a reddish brown and a greenish brown or whatever, and you use those primaries to mix your results. And of course, you might not have the exact results because the CMYK primaries weren't chosen by accident. They're chosen because they have a really good range when you put them together. If you pick primaries that have less of a range, then you will have a smaller color space. If you add orange, green, and violet, and you work with 7 primaries, then you will have a bigger color space. Now, a lot of digital printers now have that, and the goal of that really is to be able to print a bigger range of RGB colors, or to accurately reproduce a lot of spot colors that aren't reproducible with a standard CMYK profile. So that's a whole bunch of information. Like I said earlier, if you have any more questions, if you want to talk to us about your workflow, feel free to drop us an email and to start the conversation. Of course, there will be more 4 Pees Cafés. Next week, we have a case study looking at automated sheet optimization and imposition, essentially. And the week after that, David will talk about PDF standards and which one, like PDFX or GWG, you're supposed to be using.
Correct. So if you haven't subscribed to those yet, you can just go to fourpees.com/events and you will find the agenda for the coming weeks. Just register, and there's more than enough space there. So the case study next week is about the use of IMP and software around IMP to do sheet optimization in a fairly impressive way, I believe. It is a Polish printer, and the partner that did the integration at the printer is going to talk about that, both from a technical point of view, but also from what they accomplished in terms of results. That should be interesting. Well, it is interesting because I already know what he's going to talk about. And then the week after that is, like Michiel said, mostly about pre-flight and PDF standards, and which of the ones that you in the end should use, because there are like, something like 15 different PDFX flavors you can use by now. And probably close to 40 different Gantt group specifications that you could use. So which of those do you use is the topic we're going to tackle on May 27. As we said in the beginning, both of those are Thursdays again, 4 p.m. Central European Time, fourpees.com/events. Thank you, Michiel, for the color talks. We might have to add some more sessions about the more advanced stuff at some point.
If there are any specific questions from people watching, I'll be glad to add
exactly. So
extra presentations.
If you missed something, or you think that additional topics could be talked about and would be interesting, don't be shy. Reach out and tell us, and we will be happy to ask you to prepare something around that as well. Yeah, and meanwhile, if you think about anything else other than color, just let us know as well. We do these sessions because we think that people are going to be interested in them. So if you do find a topic you're interested in, don't